I assume you can hear me well right at this point. So welcome back after the break. That's our last week of classes. And after that, just a midterm final. Yep. And if good, do we have a final scheduled or not? If not, maybe we should do it. Let's double check if we have an official final slot. Okay, let's start from here. So today our topic is file systems. And the idea is to understand how file systems work and essentially top to bottom. And we actually have 2 days, right? So today and Wednesday to understand, which is great. So let's spend time wisely. So if I ask you a question, so what do you think is the role of the file system in the operating system hierarchy? I'll double check the final date. I have no idea. Okay, go ahead. If someone was saying.
Persistent storage.
Persistent storage, right? Persistent storage. But you can think a little bit and you can say, look, disks also provide persistent storage. So why do you really need file system on top of a disk?
Provide some like sanity when you want to access something. So it's not just.
No, when you say sanity, what do you mean?
Organization.
Yeah, so kind of like directories essentially, right? So hierarchical, human readable names, namespaces, if you like, no names, yeah. So, and you can say, look, what about the hashtag? Because the hashtag is good enough for most cases, right? So like, especially on modern large social media networks, right? So do we really need this hierarchical organization where you say, look, there's like my home and there will be like a Burtsev there. I don't know, I still find it useful. So it's useful to organize files in this manner, at least for me. So, right, although there are many other ways to do that, right? So we have like we do this, like hierarchical organization is actually quite useful. So for example, this is what GitHub is missing compared to GitLab, right? So because GitLab has recursive, so like it has a notion of a project, right? And you can like do sub-project or like repositories belonging to a single project, and GitHub says no, you have to use organizations. Or yeah, so it's hierarchical layout somehow is still ergonomically efficient for whatever reason. Like it's hard to explain why, right? So yeah, human readable names. What else? So something related to storage. Tell me as well. Like you said, sanity. There is sanity in terms of names, right, and how you access files, so you can give them names. But there is another aspect of sanity, which is what? Remember consistency, right? So the file system actually makes sure that if you suddenly lose power or reboot, you can actually reboot into that file system and it actually will be readable again. So meaning that you cannot do something like a half write in a file system, right? And you cannot leak resources saying that, okay, those blocks on disk are occupied by some files, but those files are not reachable from the file system, from the namespace, right? So this consistency is also important. So like essentially a file system implements like a small transaction inside. So this transaction either goes through or it unrolled after reboot, right? So that's important. And there's two main reasons, I believe so, right? So you use it as a sharing, right? Because, I mean, I actually forgot about it. So because if you simply have disk, right? And you say, look, I have multiple applications accessing this disk, how will you decide like, okay, this part belongs to application 1, maybe this one belongs to application 2, and this one belongs to application 3, and this one is available, right? But maybe A1 needs a little bit more space, right? You're running into this problem. And the file system actually can make sure that a single file, right, it can be like parts of this file, kind of like a physical to virtual memory mapping, right? Or virtual to physical memory mapping, those bits of this file, which grows continuously, right? And you can read it from 0 to whatever the max file size your file system supports. But on disk, this is disk, it can be spread all over the place, and you can allocate space dynamically, right? So sharing is also an important function, right? So it kind of creates an illusion of a long disk by saying like, or unlimited disk, as long as you really not limited by the size of the file and the size of the disk, right? So maybe modern file systems, especially distributed ones, you can throw additional disks if you're running out of disk space, and they will pick up and will say, look, like you can grow files even larger, right? So, and like you say, persistent storage. So data is available after reboot, and it's also consistent, meaning that, as I said, there will be no like leakage of resources, no half-written files, right? So half-written files are there, but like in semantical terms, meaning that maybe your application was doing 2 writes, A and B, right? And it crashed after doing A. So there is no way for the file system to somehow recover the fact that you were about to write B, because we are not snapshotting the applications, although those solutions also exist, right? So you can do application level checkpoints, but those are rare and still exotic today, right? So, okay, so what is a file system? So it's a collection of data structures which are on disk, meaning that they're persistent, and after you switch the power off, everything is saved on disk, and after you reboot, you can remount the file system and again read everything in memory. And some data structures are maintained in memory, right? Because it's efficient, right? So you, like if you say, look, I will be accessing the same files over and over again, obviously it makes sense to cache this metadata about the files, about the file, and even like about the files, and even parts of the file, each file in memory, right? So something what is implemented with a buffer cache, right? So, and typically the data structures which are there, they represent the tree of named file and directories. So it's essentially like the directory structure itself, which I was talking about, this hierarchical data structures, and they record identities. So for example, if this is a file, right, some file foo, then there is some information for how this foo is, essentially where this foo is located on disk, right? So in block number 55, 77, right, and 102, for example, right? So these 3 blocks are continuous in terms of this logical space in a file, right? But the file system will contain the data structure for this mapping, saying that, okay, look, I know that part of it is in 55, part of it is in 77, and the next block is inside 102, right? So, and also file system, of course, keeps track of which blocks on disk are free, which are allocated, right? And the directories themselves are actually just special files, right? Special files on disk, right? So essentially, the names are like there is nothing special about the directories. They maintained as regular files, but we're going to see today, right? And also, file systems must support this consistency or crash recovery, right? So essentially, a power loss or a reboot of a machine, right, might interrupt a sequence of updates, right? Imagine you say, look, I'm allocating, I'm creating a new file, and first you, for example, go to a region of a file system which maintains the list of free blocks, and you say, look, I will grab one, and this block will no longer be free, right? Because I record the fact that I need this block, right? And you do a write here. That's an update to a block which contains this metadata. But this file is not really linked from anywhere. So like, for example, if this is your directory, and at some point you say, look, I will make a recording that a file with the name foo, all right, will be in this specific block, this second write, so if this is write number 1, the second write didn't happen, right? So you reboot it after it, right? At this point, you say, look, hold on, I come back and this block is already allocated, but really there is no file, right? So that's not okay. So that's why you say either these 2 writes, write 2 and write 1, will happen, or they don't happen at all. And this is what I'm saying, that the file system will maintain something what is called a journal, right? But you can think of it as a tiny transaction, which says, look, I first will do this writes here, write 1 and write 2, and after I accumulated all the writes of the transaction, at this point, I will move the writes in their physical locations, right, where they have to go on disk. And if I, for example, if I, for example, reboot halfway doing those writes, after the reboot, I will recover the information about those writes and will redo them again. So those writes will again happen, right? Makes sense. And this ensures that the file system is in a consistent state, right? Okay, any questions about it real quick? We're going to cover it in details. It's just a preview of what is like, just to give you some kind of a high level overview of what file systems are doing, right? Good. Okay. And of course, like file systems also are designed to accelerate access, because access to memory is roughly, as we know, 200 cycles, but access to disk can be up to 20 million cycles, right? Maybe this number is a little bit exaggerated in modern terms, right? But spinning disks were quite slow. Modern non-volatile memory SSDs, which are attached on the PCI bus, that's why we have E here, right? NVMe. They're much faster. They're not like astronomically fast, but roughly speaking, they will probably do that in the order of 2,000 to maybe 10,000 cycles, right? So which is still a huge drop compared to 200 cycles when you access memory, right? But what you want to do is that you say, look, if I have some locations of file or like collection of files which I frequently access, right? I want to keep a cache of those blocks in memory, right? And I will first, it's kind of like caches in the CPU, right? Before even going to disk, I will just try to look them up in a buffer cache, right? And it totally makes sense. Like it accelerates access quite a bit, right? Because it's a several orders of magnitude reduction, depending, irrespective of whether you're running a spinning disk or an SSD, like a spinning disk, like a real spinning disk, SSD device, right? This is disk. This is SSD, which is a flash, but still attached to SATA bus. And this guy is also attached to SATA. And NVMe, which is, we'll draw it like this, which is also the same flash, but now sitting on the PCI bus, right? And just by virtue of the fact that PCI is so much faster than SATA, accesses to NVMe devices are also much faster, right? So that's the difference between SSD and NVMe, by the way, right? So, okay, but nevertheless, it makes sense. It makes sense to maintain a cache of frequently accessed blocks in memory, right? Okay, and so the file system is organized as a collection of those layers. And those layers are quite typical for any file system. I mean, maybe not for a super researchy one, right, which really cutting bleeding edge of the file system research, but something what is deployed in a canonical kind of commodity Linux and Windows kernels, right, and Mac OS as well. So it contains a collection of layers. At the very top, there's something what is called a buffer cache, right? And these are the layers from the x86 file system, but as I said, they are representative, right? So you can actually trust me, you'll see similar layers in Linux. So the buffer cache essentially is responsible for actual access, communication with a disk device, right? And this device can actually talk to an SSD. Maybe there is a different disk device, or we can say it's a block device. Something what can talk to NVMe, right? And well, SSD is the same interface as a SATA drive, like maybe you have SCSI as well, right? So, and also buffer cache first, like it reads and writes data from disk. It caches the accesses, right? This is the layer which maintains the cache of most frequently accessed blocks on disk, right? And also it's responsible for synchronizes accesses to individual blocks, right? So essentially it will acquire a lock, and only one process at a time will be allowed to write in a block on disk, right? So first it will be a write in memory, and then there will be this write will be propagated down to disk, right? On top of this layer, there is a layer of this transactional layer, which implements logging and journaling, right? So it's essentially groups multiple writes into an atomic transaction, right? And I gave you an example that if you reboot, you might lose, like you might end up with an inconsistent state of a file system, right? On top of that, there will be a layer which essentially represents unnamed files, right? in a file system, files are represented as inodes, right? And inodes, they just have numbers, like number 1, number 2, number 3, right? But they don't have names, right? So, and what inode is doing, it's essentially, it's a data structure which maintains information in which, about which blocks contain the actual data on disk, meaning that, as I say, block number 0 will be found, like logical block in a file number 0 will be found in physical block number 55. Logical block number 1 will be found in like block, physical block on disk 77, right? And so on, right? So, but they don't have names. So that's why we have yet another layer of directories, which is essentially a special kind of inodes, which contains information about the human readable names and essentially pointers to other inodes. So at a high level, directory is an inode which contains the following table. It will say something like a name of a file, foo, and an inode number 15, for example, right? Which means that after that, you go ahead, read inode number 15, and this inode number 15 will contain pointers to blocks on disk, right? And this is a directory, right? And the file system, when you open it, it knows which inode contains the root directory. So essentially, this is how you, when you first mount the file system, it will say, okay, the root directory is in inode number, I don't know, maybe 1, maybe 0, right? It doesn't matter. And then it will have pointers to other directories like bus and, for example, bar, right? Which will contain blocks, inodes number, I don't know, 7 and 11, right? And then you can open inode number 7, right? This one, for example, this contains some directory bus, which contains file foo inside, right? So we'll see how it works, how you recursively descend and essentially convert a human readable name kind of starting, which starts with a slash, which goes kind of like user, directory user, then bin, and inside bin will be file, I don't know, WC, for example, right? Okay, and so this layer of recursive lookup is actually sits on top of directories, right? Because the directory itself is just one directory, right? If you want to navigate like this path space moving down or maybe moving up, right, with the 2 dots, then that's another layer of functionality which sits on above, right? You provide a string, and we saw this function already, right? And you probably remember the name. We saw it when we were talking about the exact system call. The function was called name I, which takes a name, essentially this string, and returns an inode I, right? So that's essentially yet another function which does it, right? And finally, on top of the very top layer, which exposes the functionality of the file system to the application, is a layer of system calls. So essentially you say, look, I will allow you to open a file, I will create a file descriptor for you, and inside your file descriptor table, right, I will have a pointer to the file data structure, which I will maintain in memory for this file, right? And then you can read and write files. And also those system calls will allow you to create pipes. If you have a networking stack, you'll have sockets and stuff like that, right? So this provides kind of a unified programming interface. And especially back in the days, Unix developers had a vision that everything will be a file, either a block device, a character device, or a block device, right? It didn't fly that well, right? So modern devices are more complicated. That they expose this additional interfaces through IOCTL, IO control interface, and essentially that vision kind of only halfway there, but it works for files, pipes, and sockets, I guess, right? Okay, so let me stop here again for a sec. If there are any questions about these layers of the file systems, I'll take them, but if not, we'll dive deeper into essentially the organization of the file system, and we'll start talking about the buffer cache first.
Yeah, I have a question.
Go ahead.
Is this how much does this hold across like various different types of file systems, like ext4 versus NTFS versus like Btrfs or stuff like that?
It's similar.
Okay.
So it holds, right? So as I said, like some cutting edge. NFS is a little bit a different network file system, is a little bit of a different beast because there is like a client part and a server part, right? And the server part just is a whole different thing, and the client part is as well, right? So, but it's a distributed file system, right? Or remote at least. And distributed file systems are also much more complicated because they do replication and stuff like that. But across majority of Unix file systems, this hierarchy kind of holds.
Okay, cool.
But again, yeah, go ahead.
Yeah, this layer is present in VFS, right? This is what's there in the virtual virtual.
VFS is this idea that the operating system will kind of fix the interface, VFS, and then the kernel will talk, like, we'll use the functions of this VFS layers, essentially syscalls and nami and stuff like that. We'll be using the interfaces of this layer, and each file system will effectively implement this interface and will register pointers for each function, kind of like open, read, stuff like that, right? So VFS is there in Linux and other modern kernels as well. But VFS kind of fixes the interface, allowing one kernel to work with like any file system which implements this interface, right?
But not all file system implements all system calls, right? There's something like just how like each file system can dictate which system calls it accepts.
No, like hold on. The system call layer is here. In order to even get to VFS, there is like quite a, like if you're talking about Linux, there is quite a bit of stuff which is happening before you even get to invoke the VFS, right? There are different security checks and all sorts of stuff, right? And the ironic part that many file systems also kind of call back into this kind of VFS library, which kind of runs here to implement certain functionality. That's just, again, to simplify implementation of a file system. So it got a little bit messy, to be honest, right? And a file system itself also talk to the block layer, right? And to be honest, I don't even remember at what point the buffer cache is involved. So like, I guess the buffer cache is a kernel entity, right? So the kernel will implement the buffer cache, or it's called a page cache in Linux, right? And it will try to access a page here, and only, I think, when it's not there, it will go and ask the file system to read this block or something like that. But again, I cannot say that I'm an expert in file systems, in modern file systems. Just general understanding, let's put it this way. Never hacked myself anything besides x86 and bits of Linux, but again, only shallow, like not super deep understanding of the Linux file system stack. But go ahead, ask your question. So I missed your point about VFS, to be honest.
Okay, thank you.
No. But what was the question?
No, I was just like, how does like, I have some couple of questions, like how does it know? Suppose some stuff is a device and some are files, right? Like something like a socket, like it needs to call to the socket. Like I'm pretty sure everything is an inode at the end of the day.
No. Inodes are entities of the file system. Sockets are just separated at the level of the system calls. So the kernel will route them to the network stack.
Doesn't all read and write operation go via the VFS?
All reads and writes to the file system will go through VFS. The socket interface is different.
Oh, okay. So if socket file doesn't go via VFS, it goes via separate.
Yeah.
Oh, okay. I just thought confused there.
Okay, but at least that's my understanding. Again, in x86, we don't even have the VFS layer, just because we have one file system and we don't have a socket layer altogether, right? Although we can build one. That's a good, again, homework exercise. But again, if you really care about Getting through the VFS layer is not as hard. So just get one of those books which discuss Linux organization, and you will quickly, it will have chapters on networking and VFS layers. The one which I recommend is the one by, I think the name of the guy is Wolfgang Mauer. That's a good book. So essentially, I think it's about kernel version 2.6, right? But it's still, so it's not like the bleeding edge kernel, but it's the most comprehensive book. This is it. So this book. And if you go maybe into the preview, you will see that it will have chapters on all these layers. So like, again, hopefully after this class, you will actually be able to quickly read this book. Like a lot of what we cover, I mean, Linux is much more complicated, but at least you will kind of have a high level model of what's going on. You'll be able to quickly recap and understand like what is really front cover, introduction. We don't need introduction. Contents. No contents. No contents, really. Table of contents. Sorry, like I was under impression that it should be something at the very first thingy, but you can carefully read this one, right? But you understand that. So chapter 12 is about the Linux, about the networking layer, and chapter 8 is about the file system, and chapter 9 describes several common file systems like ext2, ext3, right? Good. Just read this book. You'll get.
Yeah.
You really care about like real professional development in Linux and other kernels. Windows will do it differently, and I have no idea how Windows does it. But again, you probably can dig up a book on Windows as well, right? Okay.
Yeah, got it. Thank you.
Okay, so let's take a look again. This is kind of representative. The way those guys, Franz Kashuk, Robert Maurice, they were writing x86. They were trying to make a representative case, which kind of captures the main gist of how those file systems are developed, right? So what is inside a file system, right? So this is the file system layout on disk. So the very first block, which is block 0, right, on disk, is a boot block. And this boot block will contain information about, it actually will contain a, if I understand correctly, a bootloader, right? Because remember, this is where the BIOS will be reading the boot loader from disk, right? So essentially, that's what, when we were booting, right? So essentially, we put essentially the BIOS read this boot code from disk, loaded in memory at address 7C00, and jump to the beginning of this address, right? Essentially, we have to, the bootloader has to be compiled in such a manner that the BIOS can correctly read it, put it in memory, and if it jumps to this address, the boot block will start executing correctly, will read the kernel from disk, and everything will go from there, right? So block number 1 is the super block. So essentially, this is the metadata about the file system itself. So it contains the size, essentially the whole thing, how many blocks the file system contains. Each block is 512 bytes, right? Slightly different number, not 4096, but 512. Well, the modern file system can be configured with different blocks, but this one contains only, this one supports only one size. So, and since the file system itself will contain those multiple sections, right? Because there will be like a section where the journaling can happen, right? So the section which contains inodes, essentially it's array of inodes, and some of them are used, some of them are free, right? The bitmap, which contains, apologize, which contains information about which blocks are free and which are still available on disk, right? And then the actual data section. So the superblock will contain information about sizes of each of those sections, so, right? So number of data blocks, number of inodes, number of blocks in a log, right? So as I was saying, this logging area is an area where if we are doing the writing an actual data block, you're not going to write it directly, right? So you will first write it here, right? And then all writes, write 2 and write 3 will be accumulated in this journaling area. And then once transaction completes, essentially you set a flag here saying that's it. At that point, the file system will essentially move those writes into the actual data area replications. If you crash halfway, you're going to reboot and redo those writes. And after the writes are done, you again clear this flag saying the journal is empty. After that, if you crash, you don't have to redo any writes, right? Because there are no pending writes in the file system, right? So we'll cover journaling later, right? Inodes, essentially, as I was saying, those are unnamed files. And remember, I was drawing them as a data structure, which essentially contains pointers to the disk locations. So essentially, this one will be, for example, here. This one will be somewhere over here, right? In any order on disk, right? But the inode itself will be contained in this area. So when you open inode number 55, the file system will read the block which contains it, will read it in memory, and we'll keep it in memory for a while until you close the file. So because you'll do this repetitive accesses, so it's much faster to cache inodes in memory, right? But you get the idea. So when the file system is unmounted, when the operating system kernel is done reading and writing files, all these inodes are saved back into this inode area. And next time after reboot, you can again read the super block, read the inode which contains the root directory. And after that, you know, like you can present user with the, like, for example, remember the system call which does the change directory, which essentially changes the current directory for a process. And then when you do ls, if you don't start your ls with a slash, right, then you will be essentially starting from the current directory, right? And then you descend into those directories and essentially like list the files, right? Okay, so this is a representation of the inode on disk, which x86 is using, right? The inode, this is the entry, right? Remember, this is the entry in this table. So this is what I was drawing here in my loose way, but more specifically, right? This entry will contain the following fields. So it will have a type, major or minor numbers, number of times the inode is linked or has different names. Maybe this one has like a name foo and has a name bar, right? And when this link drops to 0, right? Remember this unlinked system call. So essentially it removes this one link. When the end link drops to 0, at this point, inode becomes free and all the data of the file will be released back in the file system, right? This means you're deleting a file, right? You have a field which contains the size of a file, and then you will have a number of direct blocks, right? So, and I will talk a little bit about them, but essentially say for small files, this will contain addresses. So for example, this is block 55 in a data area. This is block number 77. So the first 12 blocks of a file, logical blocks, right? So if the file is continuous, right? So the first 12 blocks can be immediately resolved by just looking at those 12 entries inside the inode data structure, right? So this will contain specifically 55, the next one will contain 77 and so on, right? And it saves you time because you don't really like have to do any disk accesses. You just read the inode from disk itself. Then you look that the block number 0 is on disk, it's in the data block number 55. You go read 55 and you're done. At this point, the user can access the data, right? However, imagine that your file size is larger than 12 I blocks. And at this point, you can provide different organization, but x86 does the following. It says, okay, I will have a pointer to the indirect, to the block on disk. Maybe it will be block 107, right? So this will contain 107, which contains the next 128 entries for the file. And this is the max size of the x86 file system, right? For example, a fat FAT file system on Windows, I think the last entry here would contain the pointer to the next block of indirect blocks, right? This way you can support like infinite files because you can grow this list longer and longer. But x86 says it's just 12 direct blocks here and 128, which fits in this 512 bytes because each entry is 4 bytes, right? Got the point? Do you understand how it works? Essentially, if I want to read block number 5, how will I do it? This is the file, or if you want inode, which is an unnamed file, right? Which you can read sequentially, starting from block number 0 and block number 1, 2, 3, 4, 5. Where do you have the disk, the block number on disk, which contains the logical block number 5? How do you look it up? Let me change the color here. Any ideas? So you just like read the entry number 5 in this list, right? And it will point you to some location on disk. Maybe it will be block number 66, right? And then you say, look, if I read this block number 66 from disk, and this block number 66 is in this data area, so maybe this one is 66, so you're reading this one, right? Agree with this? However, if you say, look, what if I don't want to read block number 5, but want to read block number 13, right? So only the first 12 blocks can be addressed through direct reference here, right? If you want to access entry number 13, right? So if, depending on how you count, if you count from 0, imagine it's 0, then it's 11, and then your 12, the entry number 12 will be right here. And this is the entry on disk. So maybe it's like entry number 33, which contains the actual data. Do you get it? Right? The first 12 you can read directly, and then you go descend one layer into the indirect blocks. Agree? We'll talk a little bit more about it, but I would like you to have the general idea at this point. Missed it? Is it too confusing? Okay, we'll come back to it in a second. It's clear. Okay, good. Thank you. Maybe it was too clear, so I don't have to. So what is the max file size in the x86 file system? Who can tell me real quick? What's the formula? Exactly. So 140 blocks. So you can have 12 blocks. Let me erase everything from this slide. You can have 12 blocks reference from the direct entries, right? And then you can have 128 blocks in this indirect layer. So 128 plus 12 equals 140, and then we'll multiply it by 512 bytes, right? Exactly, that's the max size. Okay, we got the inodes, right? And those are inodes on disk, right? And if you want to access when the file system, when the operating system, or like through a system call from a user, right, tries to access a specific file, the file system will read the whole block here, will extract the inode from that block, right? And it will cache it in memory. So there will be an inode representation in memory as well, right? Okay, we got the inodes. Now the bitmap. So essentially the bitmap is the area which keeps track of which blocks are in use. That's pretty easy. And the actual data area where the files or inodes are actually saved, right? So essentially inodes have pointers here, right? And those data blocks will essentially contain data for each of those inodes, right? And the size of this inode array limits the number of total files which you can have, or total unique inodes which you can have in a file system, right? Because you can obviously have different names, right? You can link the same inode multiple times, right? And again, it's just until you overflow the counter number or run out of space to keep the directory information, right? But you know, it's an interesting exercise to count it up, right? But as you can understand, like the size of this inode array is the max number of inodes which you can have in this file systems, right? And of course, like you can change this number even in x86 and redo the file system and reboot and run a larger one, right? Okay, so let's take a look now at the buffer cache layer. So we kind of understand how everything is represented on disk. Let's take a look at how disk is accessed, and buffer cache specifically provides two things. One is synchronization. Effectively, if the two processes are trying to access the same block on disk at the same time, one of them will acquire the lock, another one will have to wait, right? And at this point, we understand how locking works, right? Because we had a lecture on synchronization, right? And the second function is caching. So essentially, the very first time block is accessed, it will be read from disk, but it will be cached in a specific array, which is called a buffer cache, which will be maintained as a doubly linked list, right? B cache. And essentially, the second time you read or write this block, you're essentially reading and writing memory. So it's much faster, right? And then eventually, either when this block is evicted or when you like do a transaction and sync this block back to disk, at this point, you do the write, right? But otherwise, it's essentially like it saves you a ton of time by not having to go to the disk. Okay, so what is this buffer cache itself? Let me just switch back to red here. So the buffer cache is a data structure, right? So, and what's important here is it contains an array of buffers, which is of n buff size, right? So roughly speaking, the buffer cache contains this array, right? And each element of this array is this thing, right? And this thing will contain the actual data here. So 512 bytes of data, and then the additional elements or fields to maintain the doubly linked list, which we will maintain in a least recently used manner to make sure that if we have to evict something from the buffer cache, that block was not accessed for quite a bit of time, right? So most frequently accessed blocks will be at the head of this list. They will be like they will remain in a buffer cache longer, right? Because that's kind of logical, because accesses will have temporal locality. If you access the block once, in most workloads, you will be accessing it again and again, multiple times. So imagine you're kind of like reading a table in a database. You first write the first row, maybe takes like some fraction of a block, and then multiple additional rows will hit the block cached in memory in a buffer cache, right? So it's, again, saves you a ton of time, right? Okay, so this is the cache data itself. We also maintain a collection of flags to distinguish the states in which the block is in the buffer cache. So it can be busy or locked by some process. It can be valid, meaning that the data was already read from disk, right? And so you can freely read it again. And dirty means that it was actually updated. So it has to be written back to disk to make sure that the data which the program wrote is not lost, right? Okay, so there is a pointer or device number, because we can have a system in which we like have multiple disks, right? And again, the file system on which you sits on one of those disks, but you know, like maybe the buffer cache will essentially mix and match multiple devices, right? Although it's not happening in our case because we just running between one device. And this is the block number of a block itself, meaning that when we will be searching in a buffer cache saying, okay, do you have a block of a specific, do you have a block with a specific number cached? We'll provide this number and the buffer cache will reply with an answer, right? Okay. As I was saying, linked list. the buffer cache will contain a pointer to the head of this list, and then the entries will maintain a doubly linked list for the list of recently used blocks in the cache, right? Okay, so far so good. So the buffer cache provides the following interface. It has those functions, block read and block write, which allows you to obtain a copy of a block for reading and writing. So essentially at this point, you acquire a lock and you'll be uniquely accessing this specific block. And when you're done writing it, right? So inside the system call, for example, you will invoke the be release call, which essentially says, okay, this block is no longer locked by this process, so some other process can try to access it, right? Because processes can open the same files, right, and can modify them concurrently, right? If you want to make some like guarantees about consistency within a file, then you have to provide your own synchronization mechanisms between those processes, right? So file system will not do that, but at least you can write files concurrently if you like, right? And other accesses, as I said, will be blocked and wait until the first process will call be release. So let's take a look at the implementation of those calls. So specifically, when you do something like a be read, right, the core of it is a beget function, which essentially takes the device number, which is passed from here, and the actual block number, right? And beget will try to look up the block in the buffer cache, right? So if successful, right, if the block is cached and it's valid, meaning that the data was already read from disk, you just return the block. The lock is already acquired inside the beget. However, if it's not valid, you actually have to go to the disk and read the block, right? So this IDE read-write function will actually read the block from disk and set the valid flag, right? Okay, let's take a look at how it works. Beget itself, right, as I said, the buffer cache is a doubly linked list. So what beget is doing, it first will, and it's not the most efficient way, but it's one way to do that, right? We'll start searching for the specific block on that list, right? And there is some amortization, right? Because the most frequently used blocks will be in front of that list. So, right, so we hope that the search is reasonably fast for most reasonable workloads. It doesn't always hold though, right? So what you do here is say, okay, starting from the head of the list, remember inside the big cache, there will be a head pointer, and until you reach the end of the list, you will be essentially moving to the next pointer in that list, right? And you will be, for each element of the list, you will be checking if device matches, right? And the block number matches too. It means that this is the block you're searching for. It's already on the buffer cache on this list, right? So let me just draw you how this buffer cache is implemented, right? So there will be elements, right? Each element contains the actual cached 512 bytes of data, right? So this is 512, right? There will be a pointer to the head of this list, right? And then pointer to the next, maybe next here, and maybe next here, right? Stuff like that, right? And maybe pointer to the next here, right? So this is the buffer cache, clear? Right? Array, essentially, right? And so for each of these guys, you say, look, I'm trying to find a block. If it's already busy, it means that someone acquired a lock, right? You will release the bcache lock. So the whole buffer cache is actually locked with this giant bcache lock. So only one process can modify this list at a time. Again, thanks God, we understand synchronization now. So we understand what these locks are doing, right? So you release block, right? And you essentially, if it's not busy, it's yours. You release the lock on the buffer cache and you will return B, right? At this point, you set the busy flag here, meaning that everyone else will know that this block is locked by you, right? But you don't hold any like spin locks at this point, right? You return this block to the caller. However, if this is not true and really the flag is busy, what you do is you use the sleep function, right? And we know how sleep works. You passing the buffer cache inside, and then someone will eventually wake you up when it will be doing the release, right? Agree? And at this point, you say, look, I was woken up I will go to the loop again. I will try to do the search. Maybe this block will be, again, at this point, maybe I will be lucky and I will be the one who will acquire this block because it was released, right? Agree with this logic of this function? Okay, thank you, Vinny. If, however, the block is not cached, so you made it through the list, I mean, you would say like, what, why not hash table? Maybe hash table is so much faster. I agree, build the buffer cache as a hash table. x86 does a list lookup. Maybe hash table would be a better search mechanism because, you know, you, again, on average have a faster lookup, right? But on the other hand, you might say, look, by the way, I also have this amortization, and so my blocks will be propagate for most workloads will be in the head of the list. So you can also say claim the not the linear but close to constant time of lookup, right? In the worst case, you have to again like search the entire list, which is at this point, yeah, it's expensive. So hash table would win, right? So, but okay, so if block is not cached, right? So essentially, you say, look, I made it through the cache, and none of the blocks matches the number I'm searching for. At this point, you want to grab one of the blocks in the buffer cache and essentially flush it, saying that I will repurpose it for my new block number, right? And here you say, look, you need to essentially find a clean block, right? Which means that the busy block is 0 and the dirty is 0, because if it's dirty, you have to flush it back to disk, right? And essentially, you're just searching through the list, starting from the back, actually, right? So essentially, if you were going to the next, at this point, you say, look, I will be actually searching from the back of the list, and because this is the least recently used, the most frequently used blocks will be in the head of the list, right? And the blocks which were not accessed recently, right, will be at the end of the block, right? And so essentially you start searching from this and you say, look, this will be my victim. I will evict this block, right? And when you access the block, you will propagate it towards the front of the list, right? Making sure that you updated the fact that this block is accessed and you will put it in front, right? Okay, let's take a look at how it works. So here you say, look, what is dirty? Dirty means that the block was written, but not yet flushed back to the disk, right? Which means that the most recent copy of the block is in memory, not on disk. That's why you can't throw it away from the buffer cache. You have to wait until it will be flushed to disk. Okay, so you search, okay, cool. You found this block, which is not busy and not dirty, right? So which in their terms means clean, right? And you say assign the device number and a block number to this block and say, okay, this is now busy because I'm acquiring it automatically. And you again release the lock on the buffer cache. And if nothing, return the block to the user, right? And if you fail, and okay, x86 takes a shortcut here, you essentially panic. So there are better ways to recover from this condition. x86 takes a shortcut and says, okay, in this rare condition when I cannot throw away a block, I will just panic at this point, which is not the most graceful thing to do, but fine. Okay, so we got it. So this was the B-read, right? And I explained you that if the block is valid, you don't have to go to disk. If the block is not valid, then you have to actually go to disk and read it, right? And the question is, what happens when you release the block? Remember, because like write works similarly, right? So essentially, in order to essentially write a block, right, you first have to acquire it for reading, right? And essentially you're writing, you will update the data, right, in the block itself, and just then set the busy flag, right? And at this point, well, not set the busy, you set the dirty flag, right? And at this point, you will say, I will talk to the block device, and it will take some time because it's not instant action, right? You say like it will take some time to flush this block to disk, but by the end of this write, it will be this dirty flag will be removed, right? And the block will be clean again, can be evicted from the buffer cache. So let's take a look at what B-release is doing. So B-release is essentially releases the lock. Remember, we said, okay, anyone who is waiting on this lock will be actually woken up, right? It's a little bit annoying here because like, no, it's not annoying because all the waiters, remember, we are using the block address as a wake up number, right? So essentially, it's a signal ID, right? So essentially, whoever is waiting on this specific block will be woken up, right? And the file system, the operating system guarantees that it will only woke up those waiters, right? It's not guaranteed that each of them will like acquire a lock because there might be multiple waiters, right? And of course, you unset the busy flag saying that, okay, look, it's now free, right? But again, everything is happening here under the bcache lock, right? So we acquire and release it. And also we promote the block to the head of the list, meaning that every time we release the block, it's set at the very head of the list, making sure that this block will be retained by the buffer cache for the subsequent accesses, right? Got it? So release, again, reasonably simple function, right? So the common pattern will be acquire the block for reading, right? This will actually acquire the lock, right? Setting the flag busy, right? And making sure that this is actually cached in a buffer cache, right? So one of those blocks in the buffer cache, it returns a block here. Then you do the write, actual like memcpy into this memory location, for example. Then you do the bwrite saying that, okay, mark it as busy and flush it to disk, for example, right? So through the IDE read-write function, and then release the block. And whoever was waiting on this block can now take turn, right? So, okay, so here is a specific example from the journaling code, which essentially just slowly goes through it like transaction reading and writing blocks on disk, right? So it does first, it reads two blocks here. So, and we'll get to the specific meaning of this function, right? So we first involve bread for these two blocks, right? Then we do this memcpy, moving data from one block into another. So essentially, like, remember there's this logging area, and one of these blocks is log buffer, lbuff, and the second block is in the data area, which is a data buff, right? So we do memcpy from lbuff from this into this one, right? After we did bread, then we say this one was written. The first one wasn't written, so you don't have to do bwrite. So this one is marked as dirty and it's flushed to disk. Agree with this? And then you release both blocks, right? So we'll get back to this next on Wednesday, right? And we'll take a look through this detailed implementation of transactions, right? Right now, our idea is to understand how the buffer cache works, right? Okay, let me stop here for a second. Are there any questions about it, about the buffer cache?
So the buffer cache writes everything to the disk on every write?
Right, this implementation of a buffer cache, because we just saw it, right? So when you do bwrite, essentially it flushes the write to the disk. And you can, yeah, which might be suboptimal in some cases, but in most cases, look, because when you do writes, you'd still group them in a transaction, meaning that you say, look, there is a group of writes, W1, W2, and W3, and I want them to hit the disk at this point, because if one of them is cached in memory, right, and one of them, for example, will be flushed first, like maybe W3 block is, if you say like, I will change the implementation of our buffer cache, and when I search for the block and I can't find a block, which is clean, but I see a dirty block, I will flush it back to disk at this point, right? So it's kind of like a write back policy. It's a little bit awkward because at this point you lose consistency, right? Because you say, look, write number 3 was flushed, but writes number 1, W and W, writes number 1 and 2 were not flushed. And after, if you lose power at this point, your file system is in consistent state. So maybe you lost it. Like in my example, we were losing a disk on file because we lost the write into the directory, for example, right? We only wrote into the free, like the bitmap area, right? Agree with this? That's why those writes are actually, they are grouped in a transaction and they all hit the disk at this point, right? And we will take a look at how writes are organized in the journaling area, but at least at this in this implementation, this is the deal. And you can kind of say, look, maybe I will have some different like organization, and I have, for example, if for the writes which participate in the transaction, right, I will flash them to disk. But for the writes which represent the data on, right, data in a file, maybe we don't create a new file, it's an old file, it doesn't grow for you just writing into those areas multiple times, right? Then maybe you can avoid essentially flushing back to disk. You agree?
Yeah, got it. Thanks.
Right, but this is a simple file system, so it just writes, flashes back. Any other questions? This is a good question though. Will we still have logs, right for those? Maybe I missed this question. So what is it about? It's a question on chat from Vinit.
Yeah, so you said we might miss some of the writes, but you said we always have logs, those transactional logs. So
Right, that's why the transaction will work in the following manner. We first update the journaling area, and then like make sure that those hit the disk. Then like there will be a block containing the head of the transaction. We say that something like there will be 3 writes in this transaction. And at this point, if we updated this and it hit the disk, the transaction will be finished after we reboot if we lose power.
Yeah.
We'll see how it works in a second. I mean, next time probably. Good?
Yeah.
Okay. Any other questions about the block layer? The real question is, which I don't really know the answer, which I should probably, is really like how those writes how often the writes really hit the disk on file systems like ext2 and 3. So probably go ahead and read this book. So I don't know the answer myself, to make sure that the real question is, can you avoid those flushes to disk essentially, right? Because typically there's like in Linux, there is the giant buffer cache, which essentially occupies all available memory, right? And there is a concurrent daemon which is running here, which is called pd flush, which essentially just slowly essentially flushes those writes to memory concurrently. So you can actually like do multiple writes into those blocks, right? And it flushes them, making them as clean. And at this point, they can be evicted, right? But the question is like, how does Linux or how does the file system like ext2 or ext3 maintains consistency? Meaning that what if like this problem, like those writes don't hit the disk? And I guess, yeah, I don't know the answer. I can try to look it up for you for Wednesday to make sure. And like, please remind me. And I hope I will be able to answer. So we can have a concrete answer for like mature file system. Okay, good. For this, move on from into the logging layer. Okay, so logging layer is essentially designed to maintain this consistency, right? As I was saying, the file system operations often involve multiple writes. And the problem is that if you're crashing, right, either you have a software bug or you have a power loss, like a hardware crash, then it might leave file system in an inconsistent state, right? So you're either leaking resources or you have an entry where you say, look, there is a file in a file system, but really the blocks are not yet allocated or double allocated, right? So kind of like, because you didn't update the bitmap area, right? So for example, here, I have this example. If crash happens during the file delete operation, it can leave the file system with either a directory entry pointing to a free inode, because if you say this inode is free, right, and the directory was not the write which updates the directory did not go through, right? So you will be pointing into this inode, like, but it will be reused for another file, right? Which will eventually cause a semantic conflict and something bad will happen in your system, right? Or you can, for example, say we did the write into the bitmap area, right? Which means that this, or into the inode area, which means that inode is allocated, right? But it's not linked by any of the directories, which means that there is no way for user to essentially access this inode, right? Which is a leakage of resources, which is also bad. Okay, so how we solve this problem, right? So I already like talked a couple of times about it. So writes don't go directly to disk. They first go into a journal, and journal is maintained in a separate area in a file system, right? At least in our implementation, and it's similar in real ext and other file systems. Although like journals might grow dynamically as be maintained as files as well, right? And once all writes are logged, essentially you first, all writes are write number 1, write number 2, and write number 3 are accumulated in this logging area, right? The file system writes a special commit record saying that, okay, there will be like 3 writes here this is all of it is a logging area, right? And at this point, we know that this group of writes or this transaction will not disappear, right? If the system reboots, after reboot, we'll essentially copy those guys into the data area one by one, right? And if we don't reboot, we just copy those blocks, right? And after we did all 3, we essentially delete the entry here, meaning that this is 0. So this transaction was committed to disk. We can start a new transaction, right? Okay, so recovery, as I was saying, so if we suddenly reboot, we essentially just reinstall those writes again, because maybe 2 of them hit the disk, this number 1, number 2, we tried number 3, we rebooted here, power loss. After we recover, we'll do the 1 and 2 again, and the third one in a third memory location. And it's okay that we roll this twice, right? It just doesn't matter whether it hit the disk once or twice, right? And after essentially we did all 3, we mark this as 0 again, saying that the log is clean, right? Okay, at a high level, is it clear how it works? Let me go into the details of actual implementation. Okay, so a typical transaction will be started with this primitive, which is called begin operation, begin disk operation, and then end operation, right? And what you will be doing is that you will say, I will use the bread to acquire the block. You will do something with this actual data, like maybe memcpi here, or actually change maybe 1 byte, right, in the data area. Then instead of doing the block write, you will do the log write, which means that it will, instead of going directly to disk, it will go through the transactional layer and will be pushed into the logging area, right? And then when you want to commit, you essentially will do end of. And at this point, we'll essentially all the writes which were accumulated in the logging area will be essentially propagated to disk. Agree? Not to disk, but to the data area. So this is the data area. Got it? Okay, let's take a look at how it works. So again, there is a log in memory, right? So it's essentially an array of block numbers and a size. It's essentially an array which essentially keeps track of which blocks numbers like maybe 55, 77 are participating in this transaction. Maybe the size of this transaction is 2, right? And also the state of the, like this log header is over here, right? And then the state of the journaling. So essentially you say there's a log which will like allow you to synchronize multiple transactions, right? Essentially the number of outstanding transactions, right? Already, because you can execute multiple transactions in parallel, because different processes will do multiple system calls in parallel, right? And it's okay. We'll commit them all at once. The flag whether the transaction is actually committing, meaning that at this point, all subsequent system calls will have to wait for this transaction to commit, right? And again, like size and start, we'll take a look at what these are, right? So let's take a look at what this begin op is doing. So essentially, it will be working with this log header, right? So you say, look, if you try to start a new transaction, you will try to first acquire the global log, spin log in memory, right? Then you say, look, if the transaction is currently committing, we can just go ahead and slip, right? We'll wait for this transaction to finish, right? Right? This is normal, right? However, there's a second case. You say, look, we're currently not committing. You check, however, so it's okay to start a new transaction. However, you have to, like, x6 essentially has a limited size of the logging area, right? And it says, I will limit the size of each transaction, roughly kind of splitting this logging area into multiple transactions, right? And then you say, look, I will be limiting the size of each transaction and the number of concurrent transactions which I can support, right? That's why it checks here that the number of outstanding transactions, like yada yada, there's this formula which computes, is not larger than the log size. If it's larger, you again go to sleep. So essentially you say, look, at this point, I cannot start in the transaction because potentially, you know, if I start a new one of those transactions may route out of spades in the logging area and none of them will be able to commit, right? So that's not okay, right? And okay, and a third case is the real case when you say, look, I actually can't start a new transaction. So you increment the number of outstanding transactions, you release the lock, right? And at this point, you're done. You register itself. At this point, you know that as long as you essentially don't go through a power loss, your transaction will finish, right? And again, like remember, we do the same, communicate with the buffer cache, get the block, update the block, and at some point we do the log write. So what this log write is doing is the following. So there's a couple of error conditions here, right, which result in panics. But again, you acquire the log for the journaling area, and you say, look, it might happen that you log write the same block multiple times. And at this point, you say, look, I will absorb this write, right? So again, remember, we are not doing the B write, which always flushes the block to disk. Here's this mechanism, which actually maybe that's the one which you were probably asking for in a real x86 file system. So if you do a file write, instead of the file write inside, will not be using the B write, it will be using a log write. And the log write might actually essentially just say, okay, look, I will check if this block was already written within this transaction. So it will be in this log header. There will be an entry for this block. If yes, I'm not going to do anything. If not, however, right, I will add, so essentially each transaction starts with, like, you maintain the size of the current log header, and you add a new entry here, right, with this new block number, right, and you mark it as dirty in the buffer cache, right? So which means that this block will no longer be evicted from the buffer cache, right? And we still release we still maintain the lock on this. It's busy, but now it will be marked as dirty as well, right? Okay, that makes sense. Okay, let me stop here for a sec, ask for questions. Did you get what is happening here?
Why is there a check of 4737? Why it be false? Why do we need to check for it? I equal to log of LH.n.
Say again. No, this is why is this a check, right?
Because when it is breaking, then it won't be true. Is it because of that?
No, because if you found the log, right?
Yeah, that's why.
If you already found it here, you can break.
But you're still writing that block.
Yeah, which is a little awkward. I agree with you. So I wouldn't write the code this way, right? So the real way, like, okay, so maybe it was, no, I don't see a reason really why would you, this is an awkward way to write this code, I agree. Essentially what they're checking for the condition whether they exited this loop with the last block number or something in the middle. If it's in the middle, it means that the block is already inside the transaction, right? But you don't really have to essentially update it again, right? Because it was updated previously, right? So you would ideally move this code over here, right? Okay, hold on. Agree with me, right?
Yeah.
Yeah, so I would put it over here. So this you don't even have it, right? So you don't even have to do the dirty here, right? And you
Yeah.
exit, like release, essentially. You just have to release here and exit, right? At this
Got it.
point. But that's not how it's written. So that's a good point. So you can actually try to do like submit a pull request, and they actually moved on a little bit with the file system. So we're sitting on a slightly older version, but you can ask them, okay, can you change it for us? Why is it done this way? So like, and maybe my slides are a little bit behind, but maybe they didn't, right? Okay, so we are kind of ran out of time to essentially discuss this last thing, which is an end op. End op will essentially enter the commit mechanism. So let's finish this end op next time, sorry, on Wednesday, right? And we'll finish the rest of the file system, maybe do a tiny review of a final exam, but hopefully like we'll have some time for that as well. Okay, so let me stop here and I will see you on Wednesday. So if there are any questions about it, I'll hang out here taking them.
So journaling is only to make sure that we recover faster, right? Instead of
no, it's to prevent like cases where like losing writes might lead to cases when you either leaking resources, like essentially marking the blocks as used or inodes as used, but really not.
But this can be detected, right? Like something like I can go through the inode entry and also the bitmap and check if something that's on the inode and something that's allocated is not, like I can check for inconsistencies.
Yeah, I agree. You're right. So let me think of an example where you cannot. So one example is, for example, you are where the real inconsistency is like use after free, this kind of example where you say this, imagine this is an inode area. And you imagine, say, this is a free, right? And there is a directory, right, which says, okay, this inode, which is inode number 55, right? This, like two writes, one write into this block and one write into the directory, right? And you should essentially kill this entry saying that 55 will not be used. I deleted this file, right? You imagine write number one goes through, you mark inode as empty, right? And this write number two doesn't go through. So you still try to access this inode as part of this. Maybe this is a full entry, right? Right? At this point, you say, look, you reboot. There is no way to, no, there is a way, right? But you have to essentially look through all the inodes and essentially match all the entries, right? Like maybe there is a, maybe you're right. Maybe there is always a way to check if the state is consistent. I was under impression that sometimes it can lead into to inconsistencies. Maybe I cannot come up with an example right now. Think about it. Maybe you're right.
Okay. I believe there is the tool FSCK or something.
Yeah, FSCK is
that
there.
I thought it was does this.
FSCK is there. The question is, so the question is to make a proof that you can always check if you are in a consistent state. You probably, let's think of an example where you may end up, for that, you need to finish this lecture to understand completely. I believe that there are ways when you can end up in an inconsistent state, which you cannot recover later with FSCK. So maybe I'm just one step away. So it shouldn't be super hard, but okay, let's take it offline maybe. For example, maybe you actually, like, there was another write, which I wanted to say deleted this directory. Yeah, let's think about it. Not sure. Anything else? Although that's a very good question, since it puzzles me myself. I should ask it on the final, to be honest. I will. Let me think about it, and I will ask. We have a couple of good questions. Next number of what? Of kind of like directories or files in a file system. And then are you always like, is there an inconsistency? That you cannot recover later by scanning the entire file system and recovering all files? Okay, any other questions? Good. Okay, let me stop here. Okay, have a good night, or I will see some of you in my architecture class later tonight.